Okay, so welcome to one of the first videos that I'm going to create for Scholarship Chemistry. This is question 3 from 2012. Question 3, 2012. I'll just change the thickness of that marker. Um, and this is all about transition metals. And this is a topic which used to be on the structure and bonding course up until 2012, which was all about the variable oxidation states of transition metals such as vanadium. And also the characteristics colors that those species have. So it's not to say that this couldn't be up in 2014 or subsequent years, because they could give you the colors and then still talk about the oxidation numbers and the various concepts of redox chemistry. But just to talk about how I'm going to approach answering this question, the first thing is that sometimes there are various ways to answer these questions. There could be two different ways to answer the same question, and as long as the content makes sense and you can back it up with equations and calculations, then you can often pick up marks in these scholarship papers from what I've seen. What I'm going to do is I'm going to go through the question myself. I also have the suggested answer from NZQA, so we can take a look at that afterwards. And then I'm also going to start off by looking at a website here, which is called chemguide.co.uk, and I just want to recognize the producer of this amazing resource. It's a guy called Jim Clark, who has been teaching for over 30 years and is a Cambridge graduate in England. So very detailed website, very good if you're looking to support your answers and your studies for your scholarship questions. It's great to take a look at this website, so you can see it up there, chemguide.co.uk. So if we read about vanadium here for a little bit, vanadium has oxidation states in its compounds of +5, +4, and +3, and +2. So if we look back at the question here, then they're talking about those oxidation states, because in VO2+, the oxidation state of vanadium there is +5. In VO2+, where the 2 plus is the charge, the oxidation state of vanadium there is +4, and then obviously it's +3 and +2 there. So this is the first thing we notice, is that we're looking at the 4 different oxidation states of vanadium. Let's go back to our theory here. So this section looks at ways of changing between them, and it starts with a bit of a description and then goes on to look at the reactions in terms of standard reduction potentials or standard electrode potentials. So the usual source of vanadium in the +5 oxidation state is ammonium metavandate, NH4VO3. And they mention this species, NH4VO3, or ammonium vandate, this species here. They mention this species when they talk about the question further down. So if we just skip on to the second part, so we just scroll down a little bit. So they mention ammonium metavandate right here. So there you go, ammonium vandate or ammonium metavandate is the source of your species there, VO2+, all right? So the solution, this isn't very soluble in water and is usually first dissolved in sodium hydroxide. The solution can be reduced using zinc and an acid. So again, both of these species are mentioned in the question. So if we go back again here, and we have acidic conditions, all right? And also, later on in the question in part 3, they mention the use of zinc. So we'll come back to that. We'll just list that right now. There we go. So it's still in part 2, rather. So they're using zinc there. So both the VO2+, VO2+ ion can be reduced by either using zinc or an acid. The exact vanadium ion present in the solution is very complicated and varies with the pH of the solution. The reaction is done under acidic conditions when the main ion present is VO2+, called the dioxovanadium ion. So often what happens in scholarship papers is you're given new species like this that you may never have seen before in your regular chemistry classes, but you have learned enough of the theory, you've learned how to assign oxidation numbers and understand reduction potentials, etc., to deal with this content. Some of this stuff is new to me as well, to be perfectly honest. Now, so the VO2+ ion is right there, the dioxovanadium ion, or the ion where the vanadium is in the state of +5. If you do the reaction in a small flask, it is normally stoppered with some cotton wool. This allows hydrogen produced from a side reaction between the zinc and acid to escape. At the same time, it stops air from entering. And we'll talk about this when we're doing another part of the question, because oxygen can also act as a reducing agent as well. This prevents reoxidation of the lower oxidation numbers. So in that case, then it would be acting as an oxidant rather. So this prevents reoxidation of the lower oxidation states of vanadium, particularly +2, B2+, by the oxygen in the air. The reaction is usually warm, so the changes happen in a reasonable time. So they show you some colours. Now these colours are important to know for this question. The VO2+ state is yellow, and then it goes through a bit of an intermediate stage where it looks like it's green, but the green colour is a mixture of the original yellow and the blue that's being produced. Now the blue that's being produced is VO2+, where the charge is the 2+. And this is mentioned in the question back here. So if you go to the question, they talk about a blue solution right here. Right, so the blue solution is due to the VO2+. Now this question gets really confusing because you start mixing these two ions up. But this is the VO2+ ion, whereas this is the VO2 oxygens in charge of +1. So I'll just refer to this as +1 and +2 in future. Okay, so that's blue in colour. We move on down. There's a little bit more theory here we want to read about. The other species. Where are we going now? Here we go. So reduction from +4 to +2. So this would be from the VO+2 ion, or species rather, down to the VO. So it's the VO2 +1 down to the VO2+, and then 3+ and 2+. So in any state, it's better just to look at them written here. So you start off with your blue, which we just produced before. We further reduce that down to the +3 state, which is a kind of a, I suppose, a duck egg blue, and then the +2 here, which is a violet color or slightly purple. All right. So there's various other chemistry you can read about there if you want to get further information. There's one other thing which is important then for the last part of this question, which is the fact that you can reoxidize the vanadium 3+, or the vanadium 2+, the violet species, quite easily. So the vanadium 2+ ion is very easily oxidized. If you remove the cotton wool from the flask and pour some solution into a test tube, it turns green because of its contact with oxygen in the air, and it's oxidized back to the V3+. So that's the situation here. Take that away. So you have your violet V2+ being oxidized back to the V3+. So that's why you need to keep the cotton wool on the top of the flask. So, of course, if you had the luxury of having all that background information, then this question would be quite doable. They also expect you to use equations where appropriate. If you really want to get the best out of these answers for your scholarship questions, you want to be writing equations wherever possible, and also performing calculations wherever possible. So let's get stuck into this question. Okay, so question 3A, 2012. Vanadium is a transition metal that exhibits a range of oxidation states. These are summarized in the Laptimer diagram below, which includes the standard electrode potential in volts for reduction of successive vanadium species. Values are given for pH equals 0, and this is, we know that's important now because pH affects these different oxidation states. So compare the relative oxidizing and reducing strengths of the 4 ions listed above. So what I ended up doing was, well, first of all, I wrote a definition or a statement. So basically, the statement is the larger or higher the reduction potential. So the higher or larger the reduction potential, the better a species is at. That's how I like to put it. So I teach students that reduction potentials are the potential for a species to be reduced. Technically not perfectly correct, but it helps you just to remember how to rank these. So if you remember that the higher the, so the higher or the larger the E0 value, the better an oxidant. So it's the potential to be reduced, therefore that makes it an oxidant. So all I did here was, now if you compare this to the answers from NZQA in a second, it's slightly different, but the way I did it was just to rank them like you get in a textbook or sometimes in the old externals for level 3 redox. So you're going to have in all cases, these are the really big reductions. So you start off with VO2 plus 1, all right, and that's being reduced to 2 plus, because it's going from plus 5 to plus 4. All right, so the reduction potential for that is plus 0.99 volts. So you'd have your E naught written above there. The next one down then is VO2 plus. So you've just formed that with a charge of plus 4, or an oxidation of plus 4, rather. And then that's going to V3 plus. And then the E naught value for that, or the reduction potential for that, is plus 0.34 volts. And then to reduce V3 plus to V2 plus, that is minus 0.26 volts. Okay, so compare the relative oxidizing strengths and reducing strengths. So we said that the larger the reduction potential, the stronger the potential for it is to be reduced, therefore it wants to be a good oxidant. So oxidizing strength is increasing this way. So this is oxidizing strength increasing this way. And therefore reducing strength is increasing down this way. Reducing strength. Okay, so that's my answer for just for dealing with part 1 there. Compare the relative oxidizing and reducing strengths of the 4 ions listed above. Well, from VO2 plus to let me just get some names for these. Okay, to save confusion from now on, I'm just going to call this species the V5 species, and this is going to be the V4 species. So to get from the V5 species to the V4 species, it's plus 0.99 volts. To get from the V4 species to the V3 species, it's plus 0.34 volts. And to get from the V3 species to the V2 species, it's negative 0.26 volts. Now let's compare that to what the NZQA guys wrote. So for part A there, V2 plus is the best reductant, so it's at the bottom, so that matches up there. Readily oxidized to V3 plus. VO2 plus, so the V5 is the highest value for E naught, so it's the best oxidant, and that's what we have up there. So the V5 plus is the best oxidant, so that matches up. It is more readily reduced from reduced than the V4 species, and V3 plus is the most stable species. That's interesting to add there, so we just add that now. This is the most stable species, so V3 plus is the most stable species. So I'm happy with that answer, and then we're going to take a look at the next part. So we continue on down. In part 2, there's a lot more involvement now. There's a lot more to do. So let's take a look at part 2. Okay, so question 3a, part 2 has a lot more to it. There are 2 paragraphs here which are essentially 2 separate parts to the question, so I'm just going to call this, let's just put one asterisk beside this part anyway. So ammonium vandate, which is the source of your plus 5 species in acidic conditions, contains the plus 5 species right there. So there you go. So this is plus 5. All right. Ion. A 25 ml sample of acidified ammonium vandate solution with that concentration was reacted with sulfur dioxide. After boiling off any excess reductant, which is the sulfur dioxide in this case, so the sulfur dioxide is the reductant, a blue solution remained. Now, because we've read our theory before this, we know that the blue solution must be due to the VO plus 2 species, which is where the oxidation state of vanadium is plus 4. This blue solution required 21.38 mils of that particular concentration of acidified potassium permanganate to give a pink color to the solution. Now, pink color, pale pink color, is due to the Mn2 plus of the manganese ion. So that's our information there. So from this information, we need to write some appropriate redox equations And then we need to do the particular calculations to essentially work out the concentration of the blue species here, the VO2 plus. We need to work out the concentration of that because that's what the idea of the whole titration was about. So here's the chemistry. The first part then is the So2 reductant. Okay, so SO2, the action of the SO2 reductant is to produce the blue VO2 plus ion, because that's the ion that we need to produce to then titrate with the permanganate. Right, so we must find a way to produce this ion. So it's done by reducing the +5 species with sulfur dioxide, and this is the chemistry. So the blue solution, so I just wrote this as a statement, the blue solution due to the VO2 plus ion is formed by reacting the V2 plus ion, which is from your ammonium bandate, your NH4 VO3. So the V2 plus ion is the VO2 plus ion, the +5 species, is formed by reacting the +4 species from the ammonium bandate with sulfur dioxide. Okay, the vanadium in the +5 species is reduced from +5 to +4 in the +4 species by the sulfur dioxide, which would have been +4 initially, which is oxidized itself to SO42 minus, your sulfate species, where it has an oxidation state of +6, and this is colorless. So that's the chemistry for the first part. So once that reduction has taken place by the sulfur dioxide, we now have our blue +4 species. So our blue solution, the +4 species is right there. And we're going to take this now and we're going to titrate it with the permanganate as per the question. So if we scroll on down here, so this is the titration of the VO2 plus with permanganate. And the concentration of permanganate we have here back in the question, we have 0.0216 moles per liter, and it took a titer volume of 21.38 milliliters to reach the equivalence point. Okay, so now we need to work out the mole ratio, and there's two ways to do this, because originally we were told also that the concentration of the ammonium bandate, which was the source of this species, its concentration was 0.09, and that was the volume of 5. So you can do this either of two ways. I'm going to do it my way first, so let's just call it my way. All right, and then we'll take a look at how the NZQA guys did this answer. So the way I liked to do this was to look at some equations. So the chemistry is that if you go back to the question, they talk about the blue solution changing at the equivalence point to give a pink color, which is due to the Mn2 plus. So what we have is we have the permanganate going to its Mn2 plus species, which is pale pink. Okay, and then the other situation we have is the blue species is being converted to back to the VO2 plus, so the +5 species. So from +4 to +5, that's oxidation, and then from the MnO4 there to +2, that's reduction. Now, how do I automatically know to say that the permanganate is going to be the species which is reduced? Well, in the question, if we just scroll back up here, they tell you the reduction potential of permanganate. If we can find it. It's up here somewhere. Oh. Okay, so I've just been looking for the reduction potential value for permanganate. We'll use purple just since it's purple in color. So to reduce the permanganate from +7 in permanganate to the manganese ion, that's a reduction potential of +1.5 volts. It's one of the highest on the electropotential list that you can have. So if we go back up just to our little list we had here before, reduction of permanganate MnO4 minus to Mn2 plus was, what was it again, plus 1.51, all right? So that's much higher than any of the other species. So in any case, the permanganate is the species which will be reduced, and then the other species will be oxidized. So the situation we have here for our part 2 question is the permanganate is reduced to the Mn2 plus, which accounts for the pale pink color, and then the +4 species, which we had as the blue, is oxidized back to the +5 species. So that's why I'm able to write these equations that I'm doing down here. So let's return back down to my equations. So we've initially reduced our +5 species to our +4 species, and now it's blue in color. We take that blue solution and we titrate it with purple permanganate, and eventually it turns pale pink at equivalence point. So here are our two half equations. So if we balance all these equations out, we end up with 8H plus here, plus 5 electrons, and then your 4 water molecules. So the amount of times you write that in redox chemistry is exhaustive. And then over here we have our, we should have plus 2H plus here, and then plus an electron. And then over here we have H2O plus your VO2 plus. And then what we need to do is just balance out these electrons. We times everything by 5 here. So we have 5H2O, let's just use a different color. 5H2O, 5VO2 plus, 5 of that species, and then that becomes 10, and this becomes 5. When we do the balanced equation, it becomes H2O plus permanganate plus 5VO2 plus going to Mn2 plus 5VO plus 1 there, and then plus 2H plus. So that's your balanced equation. Now what the equation tells us then is it tells us that 1 mole of permanganate is reacting with 5 moles of the blue stuff, 5 moles of VO2 plus, and that's your mole ratio. Remember, this is the blue one, this is purple, and at equivalence points this is pink. So we've established our mole ratio. Now the NZQA guys, if I just quickly look at their situation, they established the mole ratio by just looking at the numbers that you were given originally. So if we look over here, originally the moles of VO2 plus you were given, the concentration was 0.094, and then they took the volume, which was 25 mils, and then they get the moles of the blue species. So they're making a bit of an assumption here. They're assuming that from the VO2 plus ion, you get the same amount of your VO. So the +5 species, you get the exact same amount of the +4 species. So that's a bit of an assumption, and I didn't want to make that. I wanted to go through the equations, but it actually works out the same way from the equations. So they're assuming that the ammonium bandate, the concentration that you start with, gives you exactly that same amount of the VO2 plus species. So you have that moles, and then you just work out the moles of the permanganate using the numbers that you're given there. So the volume was 21.38 mils, and the concentration was 0.0216 moles per liter, and that gives you that moles right there. And then that works out to be 4.62 is to 23.11, and that's a 1:5 mole ratio. Now, they do say, I was reading through the reports for the scholarship answers, and they say that you should use equations wherever possible, so that's why I took the route that I take here. So if I go back to my question, I have my mole ratio of 1:5, it's a q3a answer. And then we just work out the moles, so the moles of manganate, the original concentration, so we're using this situation here. I don't want to rush these questions because I want to help as many people as possible. So the moles of permanganate will be equal to the concentration times the volume, which is equal to 0.0216 moles per liter by 0.02138 liters. Also, with reading through the recommendations for the NZQA answers, they want you to use appropriate significant figures. So typically that's to 3 significant figures for NCEA. And also keep your units there. So that becomes 4.62 by 10 to the minus 4 moles. And that should match up with what they had there. There you go, 4.62 by 10 to the minus 4 moles. So that's your moles of permanganate. And then our moles of the VO plus 2, the plus 4 oxidation state species, will be equal to your 5 times that, basically. So times that by 5. We got that from our mole ratio up there. And that becomes 2.31 by 10 to the minus 3 moles of the VO plus 2 species. And then the concentration of that is equal to, well, concentration is moles divided by volume, which is equal to, so you take your 2.31 divided by 0.025 liters, and that becomes 9.24 by 10 to the minus 2 moles per liter. And that's your concentration of your VO plus 2 ion. So as far as I'm concerned, that's a nice in-depth answer to that first part, and we're still only on the second part of this question, so you really need to know your stuff to rip through these questions in enough time. But having said that, of the 5 questions in the paper, sometimes they can have 6. There's 40 marks in total, and you just need to get over 20, as far as I understand, to pass these papers. So you can try and just do 3 really good questions and focus on doing 3 really good questions. But okay, let's keep going. So as far as I'm concerned, I've done the first part of question 3a, part 2. So I've done this part here. The second part now is another 25 ml portion of ammonium bandate solution was shaken with a zinc amalgam. So when they say ammonium bandate solution, we're still talking about it being a source of the plus 5 species. Alright, so this is the species we're talking about here, was shaken with a zinc amalgam. Now, zinc amalgam is essentially just a source of solid zinc to give a violet solution. Now, this is the giveaway here. The violet is due to the V2+, so we talked about that in our theory lesson at the beginning. This solution was titrated under an inert atmosphere. Inert is important because you don't want it to oxidize, no oxidation, with atmospheric oxygen, so that's why they mentioned that. With the potassium permanganate again, and this time the titer was 64.14 mils to reach the endpoint. Count for these observations. Alright, so in any case, we're talking about VO2 plus going to V2 plus, and then the zinc, its partner is Zn2 plus. So let's start looking at the chemistry here. Scroll on down. Okay, so in this second part of the question, where they talk about the zinc being oxidized and the plus 4 species, the VO2 plus 1 being reduced, the first thing we can say here is that the E0 value of the VO2 plus is the largest. Because if it's the largest, that means it's reduced, so it's reduced to its next species in the latimer series, which is the um, BO3 plus species, and then eventually the B2 plus. So it's reduced all the way down to the V2 plus species because they talk about a violet color. And this means that its E0 value is largest or greater than the E0 value of Zn2 plus being reduced to Zn. So our equations that we can write here are the zinc amalgam, or solid zinc, is being oxidized to Zn2 plus, and that's just plus 2 electrons, so that's oxidation, half equation. The VO2, so this is where it's plus 4, this species is being reduced to the V2 plus species, and that's plus 3 electrons and plus 2 H2O. Okay, that's the reduction half equation. Reduction half equation. We then just complete those equations out, so we get a different color here. So you need to have the same number of electrons, we times that by 3 and that by 2, and then this becomes 3 zinc, 3 Zn2 plus, and 6 there. This becomes 2, 6, 2, and 4. And then the equation is 3 Zn, that's your zinc amalgam, plus your 2 of the plus 4 species, plus 8H plus. Yes, I see where this 8H plus is from now. I'd written it's because I forgot to put 4H plus here originally. Times that by 2 becomes 8. So that should have been 8H plus just right there. So then you've got plus 8H plus. Then you have 3Zn2 plus, plus 2V2 plus, plus 4H2O. Okay, so in any case, that's our balanced equation for what's happening in the second part of the question. Now the question here then is, what is the concentration of V2 plus? Because they're talking about, the question goes on to say, when you produce your violet colored solution, this solution was titrated under an inert atmosphere with the permanganate solution, and 64.14 mils of the permanganate were required to reach the endpoint. So we want to know the concentration of the V2 plus present in purple or violet species. So in this case, again, we need to know the mole ratios. So you have 64 mils was the titer of permanganate required, and the concentration of permanganate was 0.0216 moles per liter, the same that we used before. The moles of permanganate, in this case, required. And again, we're still using our triangle: moles, concentration, volume. So moles is concentration times volume, which is equal to 0.0216 moles per liter by the 0.0641414 liters. It comes to a mole of 1.39 by 10 to the minus 3 moles. So that's our moles of permanganate, and then we need to figure out how many moles of V2 plus we have. So again, an opportunity to write some equations. So let's do it. In this case, the permanganate is again the strongest reductant, strongest oxidant rather, by far. So it wants to be reduced. So it's reduced to its Mn2 plus species. And then the V2 plus is therefore going to be oxidized back to the V2 plus species. If we do these equations out, you have the same as usual, 8H plus, and then over here we have 4H2O, and we have 4H plus 3 electrons, and then we have 2H2O. And we want to balance the electrons up, so we times that by 3 and that by 5, and that becomes, let's just use a different colored pen again. As I say, I don't want to rush these, I want to give full explanations. 3 permanganate, 24H plus, 15 electrons, 3 manganese, ions and 12 H2O, and down here we have 5 V2 plus, 10 H2O, 5 VO2 plus, 20 H plus, and 15 electrons. So the electrons now cancel, and so we have 3MnO4 minus plus 5 V2 plus 4 H plus going to 3Mn2 plus 5 VO2 plus 2 H2O. Let's see if we have any space left. Okay, we're going to have to squeeze this in here now. So from that equation, we know that we have 3 moles of permanganate reacting with 5 of V2 plus. So it's 3 is to 5 ratio, mole ratio, or if you simplify that down, 3 into 3 goes 1 times, and 3 into divide 5 by 3, and it goes 1.67 times. So it's a 1 is to 1.67 mole ratio. So then we knew that we had 1.39 by 10 to the minus 3 moles of permanganate, which if you times that by 1.67, that gives us moles of 2.31 by 10 to the minus 3 for the V2 plus. And then if you work out the concentration, the volume of V2 plus, we'll just do this down here really quickly. So we want to get the concentration of V2 plus just to finish is equal to its volume, moles divided by volume, which is 2.31 by 10 to the minus 3. To be 9.23 by 10 to the minus 2 moles per liter of V2 plus at the end of that titration. So that is part 2 completed. So let's take a look now at the third and final part as far as I'm concerned for this question 3. There is another part 4, but it's slightly different content, so we'll deal with that in a separate video. So part 3. Okay, so for this final part of the question, which is a little bit tricky, but it's based on the premise that the V2 plus solution, so the violet solution which contains the V2 plus species, is very unstable. So it's unstable. We talked about that before. So an alternative to using an inert atmosphere for the second titration is to quickly decant off the V2 plus solution into an excess of ammonium vanadate, which we know contains the VO2 plus ion. This is where it's the plus 5 oxidation state. And there's a reason for doing that. So the point here is that if your V2 plus is exposed to oxygen, atmospheric oxygen will act to convert that to V3 plus. So the V2 plus would go to V3 plus, and then the O2 would go to O2 minus. So this is from 0 to -2. So that's reduction. So the oxygen would be reduced itself and then would oxidize the V2 plus to V3 plus, oxidation. And the V3 plus is the most stable of all the species in the series. We had that before with our theory. So we want to prevent this reaction. So we want to prevent this reaction or this oxidation. And in the previous experiments, we had cotton wool on the top of our container to keep that oxygen out. So in this case, we're taking the cotton wool off. We're not using an inert atmosphere. Instead, we're introducing the VO2 plus ion, so the plus 5 species. And the idea here is that if you introduce that, you'll get VO2 plus being reduced to V3 plus all the way to V3 plus. And then your V2 plus species will therefore also be oxidized to V3 plus. And then in that way you convert all of your V2 plus to V3 plus, which is far more stable and not susceptible to oxidation by the air. So this equation balanced would be plus 2H plus right there, and then plus 2 electrons, and then 4H plus here. And then at the bottom we have 2V2 plus, 2V3 plus, plus 2 electrons. 2 electrons. And that equation comes to, so this is reduction, this is oxidation, and then you get 4H plus VO2 plus 2V2 plus going to 3V3 plus 2H2O. So what you're actually doing now is that you know the relationship between your VO2 plus and your 2V2 plus, and what we're going to do is it's essentially a back titration. You're going to determine the concentration of VO2 plus using the permanganate, and then the concentration that you get for VO2 plus is going to be equal to the concentration of V2 plus. Because we did this before in our previous calculations, if you look back through the calculations, we actually discovered that the concentration of V2 plus titrated against permanganate gave a value of 9.23 by 10 to the minus 2 moles per liter. And when we did the titration of the VO2 plus versus the permanganate, we got a concentration of 9.24 by 10 to the minus 2 moles per liter. So essentially what we're doing here is we want to react all of the 2V2 plus, we want to react all of this stuff with the VO2 plus, and then it converts it to stable V3 plus, and then we determine a direct determination of the concentration of the V2 plus using the VO2 plus manganate. So it's essentially the essence of a back titration. And we work at the concentration of the VO2 plus, and then that is equivalent to the concentration of the V2 plus. Okay, so that's the end of that question. Now these questions get quite tricky, but the next part is all to do with amino acids, so we'll do a separate video on that.